Greetings everyone, welcome back into Trig, and now it's time to take a little sidestep for a moment to talk about the last couple of sections for a test 4 review, and then there's one small little unit left that I usually put just on the final exam. This particular test is going to be on all of the laws of sines and cosines and the applications of those, along with the area formulas like Heron's formula that goes along with law of sines and law of cosines. Then all of the things to do with vectors that are applications from trigonometry. So that would be everything from creation of vectors to measuring things with vectors to having unit vectors and other applications of just the basic vector itself. And then the dot product of vectors is a whole other important section, and all of the applications that come from dot product, just calculating it all the way to angles between vectors, the projection of a vector onto another, and then applications of projections and dot products inside of inside of these word problems. Okay. As usual with these reviews, I stress that you do not focus on the individual problems themselves. Do not memorize the problems. Try and see if you can work these while I'm working them, because at this point you should have already experienced and practiced. Okay? Try to get the majority of the skills itself, right? As I said, don't focus on the problems themselves, but the skill that it takes to put the problem together, okay? The method more than the individual. So for our first problem, let's look into the law of sines. Calculate any missing pieces to the triangle. And remember, triangles just have 6 pieces of information, 3 sides and 3 angles. And you can tell right away when you have a law of sines if you have a complete pair, big A, little a, you see. And then I have little b sitting out there by itself. Now, of course, that's not the only situation that you could have that. But this is one of the ones I nicknamed the ass case because it is more trouble. The angle side case is the one case in law of sines where you can have multiple groups of answers. In other words, there is a possibility that there's more than one triangle that solves this situation. Okay? So that's the first thing we're going to figure out is how many triangles should we be expecting? And we'll figure that out sort of in a step-by-step staging process here. Okay? And then we'll finish out whatever pieces we need for whatever situation comes about. So I notice right away that I've got big A, little a. So for law of sines, right? Law of sines, I know that I can do the sine of A over little a is equal to sine of big B over little b. So I'm going to use this setup with the pieces of information that I have here. And I'm going to have the sine of 28 degrees over 35, and I'll leave the units until after. And the sine of b over 46, which of course from here I can solve for the sine of b and say that it's 46 times the sine of 28 degrees over 35. Of course, I did this by multiplying by 46 on both sides, and it gets rid of that. So I have the sine of b here is equal to this calculation. Okay? Now remember, this is where the ambiguity comes in. The fact that I have the sine and it's going to be equal to some positive value. Well, wait a minute, Simon, how do you know that's positive? Because 28 is acute, right? So the sine value here is going to be a positive output, and therefore this is going to be a positive number altogether. So this sine right here could actually come from 2 different quadrants. The size could be acute, or it could be quadrant 2 obtuse, right? The value of b here. So let's start with the way we always solve it, right? We find the reference angle, and the reference angle is the quadrant 1 answer. So I'll actually start it out this way. B1 is going to be equal to the inverse sine of 46 sine 28 degrees over 35. And of course, I'll put that in the calculator just like that. It'll just have some extra parentheses around the numerator and around the 28 when I do that. Got my handy dandy time saver here because I don't want to do arc sine by hand. That would take way too long. Okay, so I have inverse sine 46 sine 28 divided by 35. 38.09. We'll use 1 decimal point here and say that this is approximately 38.1 degrees. Okay. So then, what's the other possible angle? Or B sub 2, right, is going to be 180 degrees minus B sub 1. Because remember what we said a moment ago, solving this just like a trig equation from last unit, right? Since this is a quadrant 1 answer, the quadrant 1 answer is also the reference angle. So I'm finding the quadrant 2 answer by applying the 38.1 here as a reference angle, okay? And if I do 180 minus that, let's see, 150 minus then the 8 gives me 142, then minus the 0.1 gives me 141.9. degrees, right? Double check. 1, 2 plus 8, and then 3 plus 5, yeah. Okay, so the 38.1, this is definitely a good answer. If you've gotten this far, you know you have at least 1 triangle's worth of answers. If this thing right here was already a no-go, you would have gotten an error in your calculator, and that would have been because this would have been bigger than 1, and all that means is that this is an impossible situation and you'd have no triangle solutions. I've got at least 1 triangle set for B1, so then I'll also have to find the rest that go along with B1. Okay, now let's test for B2 here to see. Okay, how do we find out if that works? Well, let's go ahead and find the C angles that go along with both of these. Since I already know and I'm in that process, let me go ahead and finish it out that way. Okay, this then implies that C1, this is capital C, the angle 1, is going to be equal to 180 degrees minus angle A minus B1, right? Because the C1 plus A plus B1 would have to be all in a triangle together. They'd have to add up to 180 degrees. Okay, so then the 180 minus those other 2 angles should give me the third, the last remaining angle, right? So 28 plus 38 is what, 66.1. And if I subtract 66.1 from 180, that's 120, 114, 113.9. Okay? So I've got C1 now. Right? Okay. I'm going to double check because I'd hate to have to come back and redo this. 180 minus 28 minus 38.1. Yep. Very good. Always good to second guess yourself, just in case, especially on a test, you know. Okay, so from here, how would I find C2? And this is going to decide whether or not this is still going to be a good triangle. Okay? Here's the thing. I'm going to know before I finish calculating this if it's going to work or not. Okay? Because remember what I did a moment ago, I added A and B1 to subtract from 180. If I add A with B2, because this is going to be the same idea, I have to do 180 minus A minus B2, because all of those would have to fit in a triangle together. Okay? So then, right now, I'm going to start by adding the 28 to the 141.9. Right? So 28 plus 41 is 69. So that's 169.9, which isn't bigger than 180. So we know it's going to work. Okay? I add the B2 with the A, and it's still less than 180, which means this subtraction is going to come out positive, and that means it's working. Okay? So 169.9 from 180 is 10.1 degrees. Okay. So I've got two working triangles, and on top of that, we've already figured out most of the stuff that we need to answer the question, right? I now have 3 angles for each triangle, and of course the 2 sides still apply to both triangles. All right? So then I just need to find the 3rd side for each one of these. Okay, let's do that. So then I'm going to do little c1, right? That means I'm going to divide it by the sine of big C1, 113.9. To avoid as much error as possible, I'm going to use the original pair over here. So that's going to be little a over sine of big A, 28 degrees, like this. Okay, so I'll multiply this to the other side, sine of 113.9 degrees. I'll just put some parentheses there for good measure. So little c1 is going to be equal to this calculation. All right, let's punch that up. I've got 35 sine 113.9 divided by sine of 28. I have that this is approximately equal to 68. It's 0.15, 0.16 if you round it that way. I'm going to leave it like that, 1/6. And that's in centimeters. Okay, so that's one of my answers. And then the same thing for little c2, right? The only difference with little c2 is that it has a different angle, big C2. So that's the only thing that's going to change here. Notice the ratio of the A angle in the A side, that's going to be the same. And I'm going to multiply, just like before, a sine of big C2, which was 10.1 degrees. Okay, so in my calculator, all I have to do is hit up and then change that to 10.1, and I get 13.07 centimeters. Because of the rounding, this is actually going to be better if I just do 1 decimal. Let's just do that. 13.1 and 68.2. Okay, so let's recap the total answers here, right? Triangle 1. We have our angles A, B1, C1, and our sides, little a, little b, little c1. So we have 28 degrees. B1 was 38.1 degrees. Big C1 is 113.9 degrees. Okay, and of course 35 centimeters, 46 centimeters, and 68.2 centimeters. Don't forget that another check for a triangle is whether or not it obeys the triangle inequality, right? And remember, the triangle inequality is any two sides should add up to be more than the third side. So if I take 35 and 46, right, that's bigger than 70, which is bigger than 68. So that works that way. If I add 40 and 60, or if I add 30 and 60, right, it's bigger than the other one. So it does actually obey the triangle inequality. And this is one solution. This is a set right here. This is one triangle that is a solution to this situation. Okay? So then you would also put or triangle number 2, which also has an angle A, an angle B2, and an angle C2. It has side A, side B, and side C2. Okay, so angle A, of course, is the same, 28 degrees. Little a is the same, 35 centimeters. Little b is the same, 46 centimeters. But then B2 is 141.9 degrees. C2 is 10.1 degrees. And little c2 is 13.1 centimeters. Again, notice that this does obey the triangle inequality, right? These two add up to be more than 13. These two add up to be more than 35. And 35 and 13 would add up to be 48, just barely big enough to be bigger than the 46. So that also works with the triangle inequality, okay? And you notice I took an extra couple of minutes here to write out the solutions. This is what I would have expected on one of my tests. If you're going to have a problem like this, you need to present your solutions, okay? Don't just leave the answers in blanks like this. Say, I recognize that there is a triangle here and that there is another triangle over here, and both of these are independent solutions to the problem, okay? So the problem actually has two quote-unquote solutions, two answers. Each triangle is a separate answer, and both are just as important, okay? Let's continue on with triangles and get the basic law of cosines application and example out of the way, right? So I've got the application, of course, to the area, and then the actual one that uses law of cosines. So how do I know that this particular triangle setup is going to use law of cosines? Well, I start by noticing I don't have any pairs, right? Big C, but little a and little b. Big C is going to be the angle in between little a and little b, as you know, as traditional with the way those letters are set up. So I don't have any way of getting any pairs for using law of sines. So then I'm going to start by finding the little side C. Then that would give me a completed pair. Okay, so to do that here, I start with my law of cosines, right? LOC, law of cosines here, is going to be c squared is equal to a squared plus b squared minus 2ab cosine of big C. Okay, so I've got my law of cosines, and I have everything I need for the right-hand side. I've got little a, I've got little b, and I've got big angle C there. Okay, so then little c is going to be the square root of, notice I'm going straight for the kill on this one. I just square rooted both sides. I'm going to do 5.6 squared plus 10.15 squared minus 2 times 5.6 times 10.15 times the cosine of 116.2 degrees. Okay, so everything is pretty much already on one side. The only solving that we did here was to move the square root into place. Okay, so this one is ready to go. I'm going to have the square root of 5.6 squared plus 10.15 squared minus 2 times 5.6 times 10.15 times cosine 116.2. Close the cosine, close the square root, double check. Yep. Okay, enter. And we have that this is approximately 13.5857. Okay, so approximately equal to 13 point, let's just go with one decimal for now, 0.6. Because it would have been 5 nines, close enough. And of course, since it's a side that's measured in inches, right, I've got side little c now. At this point, if I wanted to, I could convert to law of sines. Because I have little c and big C, I could easily just push into getting one of these with a law of sines. Or I could opt for using the law of cosines again. Right, I've got my my two options here. I could solve for A by using the law of cosines, so that would be cosine of capital A, right? But then of course I would have to do all of the solving pieces here. So then that would be equal to c squared plus b squared minus a squared divided by 2cb. And you'll notice what I did was I got rid of the negative when I divided it. That's why these are reversed as they are. Okay, so I could do this, or I could use law of sines, which would give me something like this. I would have the sine of big C over little c is equal to sine of A over little a. Okay? One way or the other, I could find big A using one of these two. Of course, this one's going to give you less typing. And some people are worried about using this one because they get apprehensive doing the angles this way because they think, oh, I'm going to get multiple answers. Here's the thing. If you've already gotten this thing set up from this situation, law of sines is going to knock out just one answer anyway. Okay? But let's go ahead and punch it both ways and you can see, right? C squared plus B squared minus A squared. C squared is going to be the thing that we just calculated squared, which is 184.57. Plus B squared, right? 10.15 squared. Minus A squared, minus 5.6 squared. Okay, so my numerator here is 256.235. I am then going to divide that by parentheses 2 times C is 13.6 times B 10.15. So I have 0.92812 for this. And then I'll just do an inverse cosine. So I get 21.85, right? So right here, I'm getting A is equal to 21.8563 degrees. Okay? Or if I set it up this way, right, what I'll be doing is multiplying the A over. So I'll have little a, which is 5.6, times the sine of C, which is 116.2 degrees, over little c, which is the 13.6, is equal to sine of A. Okay, so 5.6 times sine 116.2 divided by 13.6. I get this side is 0.36945. I'm going to do an inverse sine. And lo and behold, I get 21.68 for A here. So as you can see, they're a little bit off of each other. which one would I consider to be more accurate? Well, when I did c squared here, I didn't use the chop as much, so that could account for the differences in the angle here. Because when I did c squared, I used the original value, so it wasn't chopped at the 13.6 for this c squared here. Okay, that probably makes up for that little bit of error there. So either one of those answers would have been fine, and just for cutting in between the two, 21.7 is a good average, because as you can see, this would round up to 0.7 and this one's just a little bit higher. Yeah, so somewhere in there would have been fine, and if you would have shown the work like this on the test, I would have given you the points either way. Okay, and then the same thing for angle B. You could set up a law of sines to find it, or a law of cosines to find it, or since we have angle A, you could subtract. Here's the thing, if you have an extra 30 seconds on your test, go ahead and set up a law of sines for angle B. Calculate it, don't just subtract it, okay? Because this will give you a way to double check to see if your angles are adding up correctly. So here's what I'm going to do. I'm going to do just that. I am going to calculate angle B using another law of sines real quick here. So for angle B, instead of 5.6, I'll use the 10.15. Sine of 116.2 degrees, divide by 13.6. And that should be equal to sine of capital B. Okay? So then I'll hit inverse sine 10.15 times sine 116.2 divide by 13.6, and I get that angle B is approximately 42.04 degrees. Okay, so if we add up 42.04 and 21.68 and 116.2, 179.92, it adds up to something that would round to 180 degrees. Okay, so there's our three solutions. Let's go ahead and present them in a solution format, right? Our triangle solution will have angle A is approximately, I think we said 21.7 would be fine. And then angle B is going to be approximately 42 degrees. We could say 0.1, that would accommodate for this. We'll just say 21.8 degrees here. I'm sorry, I'm going to round up even more just so that this adds out correctly, right? And then of course we found little c, approximately 13.6 inches, right? So there's my solution to this triangle, the three angles and the three sides. Okay, I know a little bit of hand waving in here. As you can see, this one was a little bit closer, but again, that was because the way I used my calculator, I didn't have as much chopping rounding error when I punched in the little c squared there. Okay, the less error that you can use if you get good with the previous answer button on your calculator, right, that helps you get a lot closer to the actual solution there. Okay, so compute the area of the triangle. There are several ways you could go about doing this. The quickest way with the information I've been given is Heron's formula. And sometimes on this problem, I'll even put in the instruction, use Heron's formula, like that's what I want to see you do, okay? If you don't remember Heron's formula, of course, since the instructions don't specifically say, you could go a roundabout and find some other way to do it. It would take a lot longer. Heron's formula, I just need to find the semi-perimeter and then set up a quick square root, and then we're done. So the semi-perimeter, S, is just 1/2 of the sum of these, right? So 150 plus 163 plus 172. Okay. So let's see, we've got 5 and 13, 18, 485 over 2. Okay, so that's going to be 242.5 for the semi-perimeter right there, right? And of course, as usual, because I'm going fast, I want to double check myself. Plus 163 plus 172, right? Okay, so now the next bit I have to use the calculator anyway. The area of my triangle is going to be the square root of, I'm going to have my S value 242.5 times, I then have to subtract, right? 242 minus each one in its own multiplication chunk. Okay, so the 242.5 minus 150 is 92.5, right? That's, so this is S. This is S minus A. Next, I'll do S minus B, right? So 242 minus the 163 gives me 79.5. And then lastly, S minus C inside of my square root here. 242.5 minus 172, 70.5. Okay, so then the area of this triangle is approximately, let's go ahead and punch it up straight up, square root, I have 242.5 times 92.5 times 79.5 times 70.5. Okay, so I have 112.56208. This is far enough. The linear was in feet, so this is in square feet. And there's my area of that triangle. Okay. And yeah, this is an application of law of cosines. It just doesn't actually directly use it once you know the formula. The law of cosines is just needed to show that the formula does work. Okay. Now we move into the vector portion of this test. I have 4 vectors, and these questions and the next scene's worth of questions are all going to be based on these vectors or something coming from these vectors or something using the graph of some vectors. Okay, so let's start right here with these 3 questions. Give the unit vector in the A vector direction. So remember, you have some vector, and the unit vector is just the same direction, right? It's going to basically lay on top of the other vector, but it's only going to be a length, a magnitude of 1. So it's basically carrying a unit of something, right? A single unit. But it's going to preserve the directional information of the A vector, which is sometimes important. The directional information is intrinsically built into the vector, and it's a very important piece of information. It's hard to just peel out, right? So this is one way of preserving the directional information and keeping that piece of information while still getting rid of the magnitude and carrying a single unit of something. Okay, so let's do that. Let's calculate that. So remember, the unit vector, right? The unit vector in the A direction is going to be equal to the vector itself just divided by his own magnitude. Okay? So actually I'm going to be answering one portion of this next question already. So I'm going to just bounce over here real quick and answer this. I need the magnitude of A. So I'm going to calculate the magnitude of A. That's just going to be the square root of ax squared plus ay squared. That's going to be the square root of 3 squared plus 7 squared, right? So that's 9 and 49, 58. The square root of 58. Okay. So in this case over here, that's the answer for that one, by the way. We can leave it in that form. Or you could get the decimal, but in this case, the square root of 58 is a better way to leave the answer. So in this case here, I've got 1 over the square root of 58 times the A vector, right? I almost put a dot there. Don't make that mistake. It's not a dot. Okay, so I'm doing 1 over the magnitude times the vector, which means that this is going to be equal to the vector 3 divided by the square root of 58, comma, 7 divided by the square root of 58. Okay, let's get some decimal approximations on that one, because you're really not going to be able to simplify it any more past that. 3 divided by square root of 58. I have that this is approximately the vector 0.3939, 4. And then 7 divided by the square root of 58, 0.919. That'll work. Okay, so either one of those, depending on what you need this particular bit for. Okay, next we have to compute the magnitude of B, then the dot product, and then the angle between vectors A and B. So let's continue here. The magnitude of vector B is going to be bx squared, right, plus by squared. So I've got the square root of -8 squared plus 4 squared, which is going to be 64 plus 16, right? So I have the square root of 80, which we can simplify that one, right? That's going to have a 4 in it. In fact, it has a 16 in it, right? 16 times 5. So 4 square root of 5. And we can leave it there. Okay, A dot B, I'm going to be multiplying the 2x components and multiplying the 2y components and then adding together those products. So AX, which is 3, times BX, which is -8, plus AY, which is 7, BY, which is 4. So I've got -24 plus 28, which is 4, is the dot product of A and B. Now, what about the angle between vectors A and B? Okay, don't forget that the formula for this came out to be the alternate version of the dot product. The cosine of the angle theta between A and B is equal to A dot B divided by the magnitude of A and B, respectively, multiplied. Right? We're just multiplying those two numbers there. It's not a dot product. I put a dot to separate the lines so you can see it better. So notice all I'm going to do to compute this is I'm just going to take an inverse cosine of the dot product, which we've already found to be 4, divided by these two magnitudes multiplied. So that would be the square root of 58 times 4 square root of 5. And I can crunch this in the calculator and we can get the angle in between these two guys. Okay, so I've got 4 inverse cosine 4 divided by square root of 58. Okay, I'm getting 86.63 degrees. There. Okay. All right, and lastly, calculate the vector h such that h is u vector minus the m vector. Then graphically display how h can be created using the graph of u and m, respectively. So in other words, I'm asking you to do the algebraic and the geometric side of a vector subtraction. Okay? So let's start by doing the algebraic side, and we're going to compute u minus m, basically. Right? So the h vector is just going to be the vector where I'm doing the ux component, 8, minus the mx component, which is 9, comma, the uy component, which is negative 3, minus the my component, y component, which is negative 9. So then the h vector should end up being the vector negative 1 and 6. So that's the first part right there, computing the h vector. Okay, so now let's use the graphs of the two vectors u and m to create the graph of the h vector. So in other words, the h vector is not going to be graphed from the origin like u and m are. I'm going to use the endpoints of u and m to create the vector h. Okay, so here I go. I'm going to need a straight edge here. All right, vector u is 8, negative 3. So from the origin, I go 8, 2, 3, 4, 5, 6, 7, 8, which is here, and then down 3. Okay, so that's going to be here. Should be negative 3, yeah, good. Okay, so then I should have this vector here. Okay, so this is the u vector. Okay. Next, let's graph the m vector. I'll do it in blue again. 9, negative 9. Okay, so 4, 5, 6, 7, 8, right? 9 is just one more over. And then we have to go 9 down from there. Right? Give or take. Should be about right there. Yeah. Right around there. And uh-oh. Gotta call in the big guns here to get this guy drawn. Okay. So then this is the m vector, right? So then how do I do u minus m? Well, remember, the geometry works either with parallelograms or tip and tail type of things, okay? The subtraction of these two vectors is going to be somehow connecting the tips here. That's how subtraction works, right? Addition, I would move one down and then connect the diagonal. Not this time. With subtraction, you connect the tips. So then that would be something like this. Like this. And then do I put the arrow at the bottom or the top? Well, remember, in the subtraction, it's going to point at the original, the first total. So it's going to point like this at the u, because the u is in front of the subtraction. So this is vector h. Notice that it's exactly a -1 and up 6, right? It goes 1 to the left and then goes up 6 to make that h vector. So this is the graph of h, using u and m to graph it. And then, of course, this is how you calculate h. Okay? Okay, let's continue our investigation into the basic world of just constructing vectors here. I have create and graph vector r such that the magnitude is 4 and the angle of vector r is 217 degrees, and we want to write it in the ij format for the final answer. Okay, and then we have another one where I'm breaking vector m into its two components, where the components are always, you want components to be perpendicular, and one of those components is the projection of m into the other vector u. Okay, so let's start with vector r here. I'm going to create vector r. Well, remember, if you know an angle and a magnitude, it's as easy as just doing a multiplication. So that would be the magnitude of r times the vector cosine of the angle, comma, sine of the angle. Like so. Okay. So then I'll just go ahead and create the r vector. But remember, we want to do it in ij format. So I'll do, I'm going to actually do the scalar multiplication where I multiply the magnitude times the cosine and then the magnitude times the sine, and then I'll put it in I and a j, right? So then r is approximately, I'm going to have 4 cosine 217 degrees, which is negative 3.195. Negative 3.19i. Let's do that. Okay. And then do the same thing, but sine, 4 times the sine of 217, I'll have minus 2.41j. So there's the r vector calculated algebraically, right? Now let's graph this thing. If you graph this on a small sheet of paper, of course it's going to be easier, with a smaller protractor. I'll probably have to use my little protractor here because I can't seem to find my larger one. Okay, no matter. So the easiest way, I could try to go to these coordinates. To be more accurate, I know a whole number here and a whole number here. I'm going to use the actual 217 degree angle and a length of 4 to try and make this as accurate as possible. Okay, so let's do that. Let's make vector r on here. I'm going to just go ahead and graph it on the same grid. On a test, I would normally have 2 separate grids. But here I'm just taking advantage of the fact that we had already graphed vectors m and u. So it makes it easier for the bit that we want to do here. And this won't interfere with it, right? Because 217 is in quadrant 3 over here. Okay, so that of course makes it easy. Theta r is in quadrant 3. So I'm just going to do the 217 minus 180 sort of mentally, right? That's going to be 37 degrees that I would have to measure on this. Okay, So 37-degree angle upside down here. Make sure and get it rotated exactly on center. So 37 degrees. Here's 35. 637 is right there. And we want a length of 4 units. So it should be something like this. Should be my R vector, right? So that you can see the angle that I rotated here is 217 degrees, right? And then of course the length of it, I measured 4, I use an inch for each one of these things, so I measured 4 inches of length there. And let's take a look. The X component should be 3.2-ish, right? So 1, 2, 3, and then look, it's about a quarter of the way past the 3 there. And then the Y component should be close to 2.5, right? So 1, 2, and just a little bit under a half there. So that's exactly the R vector that we've computed at 217 degrees with a magnitude of 4. Okay, so now let's compute the components of M using the projection here, right? So the projection of M onto U means that W1 is going to be equal to M dot U over U dot U times the U vector, right? And of course there's other versions, that you can memorize and whatnot. The U dot U just gives the magnitude of U but squared, right? And then M dot U, of course, is the dot product, and I have to multiply times the U vector. So let's do this computation here. M dot U, I've got 8 times 9 is 72, and then -3 times -9 is 27. And then U dot U is going to be 64 plus 9. And then, of course, this is times the U vector, 8, -3. So I have 99 over 73. Times the vector 8, -3. Okay, so let's get some decimal approximations here. I've got 99 over 73 times 8. So I have 10.85, comma, that doesn't seem right, does it? Oh yeah, it does. Okay, it does. Then I've got times the -3. 99 over 73 times -3. I have -4.07. Okay, so there's the W1 vector. Let's graph that one while we're talking about it here. So I'm going to graph this, and remember the way that works is that I take the M vector and I put it at a right angle, and actually we're going to run out of space here. I'm going to put it at a right angle to the U vector here, right? So if I were to actually graph the 10.85, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, oh yeah, it's like way over here. Then I have to go down from there 4, just a little bit over 4. See, that seems like about right. It's in this direction here. Right here. That projection is going to be here. It's going to be at a right angle there in this thing right here. And the projection W1 is going to be this entire piece, right? That's W1. I'm projecting M into the U direction. Okay, so then where's W2? Well, W2, to be at a right angle of W1, needs to be the remaining part of vector M that was not projected. And the only way that you can not project a piece of it is if it's completely at a right angle. Hence, the W2 is going to be at a right angle to W1. But it's also the remaining bit of vector M, which means it would be vector M minus the W1 that we just computed. Okay, so that's going to be 9, negative 9 minus the 99 over 73 times 8, negative 3, right? I'm not using the decimal chop approximation one. I'm going to try and make this as accurate as possible here. Okay, so let me go ahead and write W2 beneath here. I'll go ahead and put it in darker color so it can see it better. W2 is going to be, I've got 9 minus 99 over 73 times 8. So this is going to be negative 1.85. And then same thing, but now it's negative 9, negative, so plus, right? 99 over 73 times 3. So I get negative 4.93. Like so. So there's the W2 vector. Of course, if you want to double check that they're at a right angle to each other, you will note that W1 dotted with W2 will give you 0. Right? So if I do the 1.85 times 10.85 plus negative 4.93 times negative 4.07, that will equal 0. Right? Let's see how close we get. 1.85 times 10.85, 20.0725 minus, or no, yeah, 4.07 times 4.93. It basically rounds to 0. It's many zeros in and rounds to 0. And that's because we chopped it here and there, right? If we were to actually do this dotted with this, you would see that it would come out to be 0, like exactly. Okay, so let's graph W2. W2 is going to be that small bit of vector that's actually parallel with this piece because it's at a right angle here, you see? But we usually typically graph it like they're coming from the same source over here. So negative 1.85, negative 4.93 should be at a right angle there to the U vector. Or, well, to W1 is in the U direction, right? So let's get that. Like that. And we're going to just under negative 2, just under negative 5. Negative 2 is here. Negative 5. 1, 2, 3, 4, 5 is here. Yeah. So you can see that dot that I put is already in line with these other two. That's about like that-ish. Here's W2. Notice that this is completely a right angle there. And the W2 and W1 vectors make up vector M. W2 plus W1 equals M. You see M would be the diagonal if you connect these up in the parallelogram sense like that. So W2 and W1 are the components of M. But they're the components of M such that I have used the vector U as a basis, as a beginning for another system, basically. And that's kind of what projection in this sense is used for. Okay? Now let's work a couple of examples using vectors. So I've got an object on a frictionless surface here, just so that we don't have to worry about extra other vectors here. Okay? I have the object is weighing 174 pounds, and I want to know how many pounds of force pulling up the ramp would it take to just hold it there. Okay? So in other words, the minimum amount of pound force that it would take to just keep it. You don't want the object to start moving, and you don't want it to start slipping back down. To just hold it in place, okay, is going to be directly related to how much the object weighs. So the ramp is at a 23-degree angle, and I want to have just a quick calculation, if I can, of how to get the piece of the weight that's acting in the same direction that I'm pulling. Because obviously I'm not pulling against the whole weight, right? That would be upward. I'm not pulling that way. But I am pulling at a slant up the ramp. So I'm going to take a component of the weight. And remember, I can create components by projection, right? So the projection vector here is what I'm looking for. What I want to do is I want to project this thing right here into here. So in other words, if I can take just take the dashed line here such that this is at a right angle, then I'm just going to be looking at the projection into the ramp here. That's the component of the weight that's going to be acting directly against me pulling up the ramp. Not all of the weight, just that projected component. Okay, well then I just need one other thing then. I need to have something to project this vector onto. That's simple enough. I'll have another vector, I'll call it the R vector, which is going to represent the ramp. So if I call this the weight vector, we'll call it W vector. If I project W onto R, then that's the vector that I'm interested in countering, okay? But also it just said calculate the force pounds. It doesn't want the actual whole vector here, okay? I know the direction. I'm not interested in the directional information. I just want to know how many pounds, what's the magnitude, what's the size of this. So honestly, to balance it equally, to keep it stationary, that means I just need to know the magnitude of this projection. So I'll only be calculating the magnitude of the projection. So the magnitude of, let me do it in this color here. I'm interested only in the magnitude of the projection of W onto R. Okay, so magnitude, you see, of the projection of W onto R. And remember, to do that, all we need to do is W dot R divided by the magnitude of R. So there's a few different little side tricks that we can do here. If I can create the R vector that represents the ramp as a unit vector, then this magnitude will be 1. and it'll be real quick and easy. Okay? And in fact, that's exactly the best way to create the r vector anyway. So this r vector is solely based on the fact that the ramp is at a 23-degree angle. So the r vector is going to be cosine of 23 degrees, comma, sine of 23 degrees. That's the r vector. The w vector is always perpendicular with the surface of the earth because it always points toward the center, right? So my w vector here is going to be equal to 0, right? There's no horizontal component. And negative 174, or you could say positive 174. The only reason I'm throwing the negative on there is to show the direction, okay? And notice the magnitude of r here is 1. Because all I've created is a unit vector. I didn't put a magnitude times the cosine and the sine. I just have 1 times the cosine and sine. So this is a unit vector. If you do the length of this, cosine squared plus sine squared will equal 1. So I've just got a unit vector for r. That's nice. And I'm just going to do w dot r divided by 1, so just w dot r. So that's 0 times cosine of 23 degrees, right? Minus 174 times the sine of 23 degrees, right? And I'm not so much worried about the negative, okay? Just this magnitude right here. It is going to be a negative quantity, but the negative is not really part of the magnitude. The negative is just dictating that it's going opposite of the way that I'm pulling here, okay? Because I oriented the ramp vector in the direction that I'm going. So the negative here just denotes that the weight is pulling opposite the ramp direction that I chose. Okay? So in fact, I'm not even going to bother putting it there. I'm just going to put a plus there because we're not going to worry about it. I'm not going to worry about the negative. 174 times sine 23 degrees. I have 67.9872. So we may as well just go ahead and say 68 pounds. Of course, if you round up too much, right, you'll end up overcompensating the force and it'll start moving upwards. So, but close enough. Close enough. Okay. Next, we have a person pushing a buggy through some store. Who knows? Maybe it starts with a W. Maybe it starts with another W. It could be Rouse's or Walmart, Winn-Dixie, whatever. It's some shopping center. We've got a cart. Guy's pushing it, or woman's pushing it, whatever. A person is pushing it, such that their arms are coming from their shoulder at a 52-degree angle from their eye line horizontal. So you have the eye line that's here. The arms are at a 52-degree angle down from that. And they're pushing with 67 newtons, right? And the shopping cart moves 15 meters. So we want to calculate the work done, okay? So there's a few different ways that you can look at this, a few different formulas you could talk about. But essentially, work is going to be force vector dotted with a distance vector. Anybody who's taken physics seem to remember work is force times distance, right? Well, when you're doing vectors, it's force dot distance, right? Okay. Well, I can actually take a little shortcut here too, because notice this vector for my distance is parallel to this horizontal here. So essentially, I could take this vector and put it up here, couldn't I? I could say that this is my 15-meter distance vector. Okay, so my shortcut is this. If anytime you want to dot two vectors, another way to do this could be that I could take the magnitude of the force vector times the magnitude of the distance vector times the cosine of the angle in between them. I'll just do FD for the theta there. And that's exactly the information we have. You'll notice I have the 15 meters, the 67 newtons, and then I have the 52 degrees between them. So the work that we're going to calculate here, I can shortcut my dot product. Instead of having to actually create these vectors and then dot them, I can just use these magnitudes. 67 newtons times 15 meters times the cosine of 52 degrees, like so. So let's crunch this up. I've got 67 times 15 times cosine 52. I have 618.74. The work is approximately 618.74, and this is going to be a Newton meter, as you can see from the units, newtons and meters. A Newton meter, right, which ends up being a joule, right, joules of energy. Okay. So let's finish up this test review with one more application where we have this type of problem that you've seen earlier in the semester, and it was worked just with right triangles. You could also work this one with just laws of sines and cosines. The fastest way is using vectors. If I represent all of the quantities with vectors, we already have all of the vector calculations set up. And you just have to make sure that you're bookkeeping your angles correctly to make all of it work out correctly. Okay, so we have a plane flying from somewhere, and it goes east for 37 miles, then turns on a bearing of south 68 degrees east, and then continues for another 46 miles to some destination. So then from there, what bearing and distance is the return flight for the plane? Okay, so we've seen problems similar to this either with boats or with people walking in woods, whatever. It's the same idea. So if we start with a normal, north, south, east, west directional. Okay, so of course this would be the north line, south line, east line, west line. And then the plane travels along the east line, right? It travels east to this point right here. And we're saying that that's 37 miles, right? I'll just label it with 37. Okay. From here, it turns on a bearing of south 68 degrees east. Okay, so in other words, it's something like this-ish. And then travels, another 46 miles here to some destination point over here. So then at this point, we want to know if it was going to fly directly back to the original point of origin here, then what would be the distance and the bearing needed on that distance to get back directly to the original point. Okay, so I'm going to go ahead and label this thing right here. Okay, let's do this. Let's make the first vector right here, we'll call that vector A. The second leg right here, we'll call it vector B. And the third leg right here, we'll call vector C. Well, the distance part is pretty straightforward. That's just going to be the magnitude of vector C. I just need to be able to create the other two vectors in order to do this here. Okay, well, vector A is very simple. It's in a singular component, right? So vector A you can already see is going to be 37 in the horizontal and 0 in the vertical. Okay? Then, to create vector B, just put a little north, south, east, west line pairing here. And remember, the bearing was 68 degrees east. So in other words, I've got this angle right here is 68 degrees. But if you see this right here as another set of crosshairs and this angle coming off of it, okay, then you should be imagining that this bearing could be generating a vector like this, right? This would be vector B. We know that this angle is 68 degrees because of the way bearing works. But that's not the angle that I would use to create vector B. Vector B, I would use this angle over here to create, right? Because that's typically our x-axis-ish type of thing, right? I would use the 90 minus the 68, which would give me 22 degrees. Okay? And actually, right, it would be a negative 22 degrees, if you want to look at it that way, because it'd be rotated down. So vector B is going to be 46 times the cosine of negative 22 degrees, the sine of negative 22 degrees, like this. Okay? And then I can say that since this is the same beginning to the same ending, notice I pointed vector C in the direction to the ending point here. I know that that's not the return trip direction, but the way I've pointed C, I can say that vector C is equal to vector A plus vector B, right? That's the tip to tail type of geometric adding. So if I can find the components of vector C, then I just do the magnitude of C and I've got the distance. It doesn't really matter which direction C is. The magnitude is going to be the same either way because it's a distance vector. Okay? So notice that I can do some finagling here. Vector C is going to be 37 plus 46 cosine of 22 degrees. Cosine is an even function. So doing the cosine of negative 22 is exactly the same as doing the cosine of positive 22, hence why I'm just adding those. And then sine is an odd function, so I have 0 plus negative, so in other words, just negative sine 22 degrees, like this. Okay? And therefore the magnitude of C is just going to be the square root of these things squared. Right? So that's 37 plus 46 cosine 22 degrees squared plus sine 22 degrees squared. And notice I had to drop the negative just because it's going to get squared away anyway. So let's do this computation. Okay? I'm going to have a square root. I'm going to open another parentheses for this. I've got 37 plus 46 cosine of 22 degrees. Close the cosine. Close the squaring. Plus, open a parentheses, sine 22, close the sine, close the squaring, squared, close the radical. And of course, if you wanted to, you could do each one of these components individually and then just plug it all together. I'm just trying to avoid error as much as possible. The magnitude of C is approximately 79.65. So we'll say miles. And that's going to be the distance of the return trip. Okay? Next, the bearing. So the bearing to this, along this line and the bearing back are identical in angle, but remember one of them will be south and east and the other will be north and west, right? If I were to draw another pair of north, south, east, west lines here, right? You would notice that this angle right here, I'll call it gamma, is the same as this angle here, gamma. Okay? Because this east line and this west line are parallel, the C would be like a transversal. So it really doesn't matter which way you look at it. I can compute this angle right here the same as I can compute this angle here. And notice the way I've labeled this angle here, that's the vector angle of vector C. Okay? So the thing that I've labeled as gamma there is the vector angle of vector C. So in other words, gamma is going to, the tangent of gamma is going to be equal to CY over CX. Right? It's just the normal vector angle of vector C. So I have the tangent of the gamma angle that I'm trying to find there. And the y component is negative sine 22 degrees divided by 37 plus 46. Oh, I wish one of you was here to catch me. I messed up. Look, it should have been times 46. Minus 46. This should be minus 46. This should be cosine 22 degrees. I need to go back and redo this calculation. I messed up. Boy, I wish one of you was here to catch me. I made this problem up on the fly, just like I make up some of my other test problems, because I make test problems just like this. I should have, probably should have worked it out beforehand, huh? Okay, here we go. My apologies. Brief intermission, fixing miscalculation. 81.49. Let's just do 81.5. Miles. My apologies. Okay, so it's fixed over here. What I'm going to do is the inverse tangent of this, but I'm going to leave off the negative. Okay? When I punch it into the calculator, okay, I'm going to leave off the negative because all it's going to do is tell me that gamma is a negative angle, which we can already see. Technically, gamma should be a negative angle. I'm only concerned with the size of it. Okay? So gamma should be approximately, I'm going to do an inverse tangent on this. Right? So I got inverse tangent of 46 times sine 22 divided by open a parentheses because of the addition there, 37 plus 46 cosine 22 degrees. Close the denominator, close the inverse tangent. Yes. 12.2 degrees. Okay, that's not my bearing angle though, right? Because even if I were leaving here and getting a bearing, remember it comes off of the south line. So technically, this angle right here should be my bearing angle, which if you're looking at this crosshairs over here is the angle this way, which is the same idea. I would be north so many degrees west. Here I would be south so many degrees east. Either way, it's the complement of that guy right there. Okay? So my actual bearing angle, I'll call it theta, right? This will be theta, which is the full thing, not to the blue line, to the purple line. This is theta right here, right? This is the bearing angle. So theta is approximately equal to the complement of this. So 90 minus 12.2, 77.8 degrees. Okay, so then I use that, bring it back over here. So it would be this distance at a bearing of north 77.8 degrees west, right? If it had asked the question, what's the bearing from the original point to this thing directly, then you would say south 77.8 degrees east. But either way, right, you can just do it that way. So using vectors simplified the way these things are coming together, as long as you know how to keep track of all of the angles and where everything's taking place. If you go all the way back to the beginning of the semester, you'd remember I did a problem similar to this with a boat, and what we did was we finished out the right triangle here and used this, the connections of the pieces between the two right triangles. In this section, you could also do some laws of sines and cosines, because you know this angle inside of here is going to be 90 plus 68, 158 degrees. You could use the law of cosines to figure out the length of this other side here. And then you could also use your knowledge that the angle up here is a 22 degree angle, and then you could finish out this triangle and then add some angles here after you computed them with the law of sines. You could use law of sines to compute this itty bitty angle between the blue and purple lines, and then you could add it to the angles. So it's the same amount of work essentially, but a lot more steps if you're going to do law of sines and cosines, or if you're going to do the two right triangles. This is what vectors do best. Since you already have a lot of standardized calculations for vectors, it really just brings it all together into, oh, you need that? Okay, so create this vector, then just do this to the vector, right? Create the vector, then do this to the vector. And then you can get a lot of that information that's already built into these vectors, okay? So I hope this review has helped you sum up all of these particular ideas for the trigonometric class, and helps you study for a test of the similar caliber, or if you're in my class, test 4. And remember, focus on the individual skills. Don't memorize the problems, because the problems do change.